Good afternoon. Welcome to the CERIAS Security Seminar at Purdue University. It's my great pleasure to introduce today's speaker, Madhu, from our neighboring institution, University of Illinois and Urbana-Champaign, where he's currently a faculty member there. Madhu received his PhD from the Institute of Mathematical Sciences, India, and spent 3 years as a postdoc at UPenn before joining Illinois. And his research interests are in verification and analysis of software with an emphasis on methods involving concurrency, logic, and automata theory.
Thank you, Ningri. So I'm going to talk about today about the role of automata theory in software verification. So feel free to ask me questions and stop me and ask me questions. I hope that's okay. So I'm going to talk about how automata theory techniques, theoretic techniques, would be useful in software verification. This is joint work with Gennaro Parlato, who is a postdoc who has just moved to Paris, and Xiaokang Chu, who is a student of mine. But it also involves work I've done over the last 5-6 years with several other people. These are the more recent recent collaborators. Okay, so some background. It turns out that automata theory has played an incredibly important role in hardware verification. So the reason is you can easily model circuits as automata where the way the circuits are flipped, whatever they have stored in them is modeled as a state, and as inputs come, the automaton, the circuit reacts, giving output on the wires, and you can model them easily as automata. Okay, so clearly circuits are finite state machines, right? So they will naturally be they can be naturally captured as automata, and what people did was also captured specifications of your circuits. Okay, if you wanted your circuit to do a particular, let's say, addition correctly, you would specify that also as automata, because they are finite state machines and their behaviors are kind of behaviors of finite state machines. You can model that as automata. And there was this very important work by Amir Pnuli on temporal logics, where reactive systems were introduced, where you think about a finite state system not as computing, taking an input and producing an output, but rather as though it interacts infinitely often with its environment. The notion of temporal logics capture behaviors of reactive systems. And there was this beautiful theorem which kind of goes back to Buki in the 60s, but was more exploited by Vadi and Wolper, where they showed that temporal logic specifications can also be compiled into automata. There's special kind of automata which work over infinite words. So I presume that most of you are familiar with automata which work over finite words, but these are automata which work over infinite words. And the model checking problem, which is checking whether your circuit satisfies a temporal logic property, was studied by Clark, Emerson, and Sefakis. It actually won the Turing Award recently. And model checking essentially turns out to be emptiness of automata, because what you do is you take your circuit and you intersect it with the negation of your specification, and you ask whether that language is empty, right? And the reason why that works is that if it's non-empty, that means that there's a behavior of your circuit which does not satisfy the specification. So you would have found an error in your circuit. Okay, so model checking really is an automata technique, and it really scales to extremely large automata. We're talking about 2 to the 100 states. You can scale this up to about 2 to the 100 states automata using 2 techniques. One is BDDs, which was pioneered by Macmillan, where you had compact representations of your automaton state space using logical formulas in some normal form called binary decision diagrams. And then you had SAT solvers, which are Boolean satisfiability solvers, which can actually search a large state space nowadays, because even though SAT is NP complete, we have very good solvers for SAT. So, so given that, I mean, given 2 Turing Awards and a Gödel Award, it really automata really is the basis of model checking. It played a very important role. But when we move to software verification, it's not clear whether these pluses of automata still remain. The immediate plus that circuits can be modeled as automata is true, but you can't certainly model software as automata because the number of states in a software is infinite or unbounded. Right. So, so I'm going to argue that automata are useful for software verification in various domains. But first, we need a definition of what we mean by automata. So I expect you think of automata as really DFAs or NFAs, right? We're going to move slightly away from that definition, and we're going to look at very, very generic notions of automata. So I'd like you to think about what are the salient aspects of an automaton. Forget the definition of an automaton. What does it really do? So what it really does is it's a finite description, right? Certainly an automaton has a finite description. It's a machine, right? So it's a finite description of an infinite set of elements. For word automata, which you're familiar with, it turns out that it's a finite description of an infinite set of words, which are the words accepted by your automaton, right? But it's really a finite description of an infinite set of elements. But that's not enough, because if you take a logical formula, right, you can also think of logical formulas as ways to express an infinite set of elements. Or you could take Turing machines, right? Turing machines also accept languages, and that's also an infinite set, right? But the most important thing is that automata come along with tractable algorithms, right? So, and Turing machines don't, general logical formulas don't, right? So automata come along with tractable algorithms. For example, emptiness of an automaton is typically, you would define automata such that the emptiness problem is decidable. Typically, inclusion is also a decidable problem. If I give you 2 automata and I ask, is the set represented by the first automaton a subset of the set represented by the second automaton? That's usually decidable. There are a lot of learning algorithms which you can usually use automata for. And these are algorithmic learning techniques where I have 2 people, a teacher and a student, right? The teacher has a particular concept in mind, and which is representable by an automaton. And it turns out that there are efficient learning algorithms for the student to get to know what this automaton really is, right, by asking questions of a particular kind, right? So automata are finite descriptions of infinite sets, right, with tractable algorithms, okay? And when we define automata over different classes of concepts, you will realize that they all fall into this category. So this is my 1-slide summary of program verification. So this is the state of the art of program verification. So above this line, I have techniques that can prove programs correct. And below this line, I have techniques that find errors only in programs. They may not be able to prove programs correct. Okay. So the one thing which you do know is testing. This is just vanilla testing. I take a program and I feed inputs to it and check whether it's okay. So testing is the most widely used form of an analysis. And testing is certainly can't prove your program correct. It can only find bugs. If your program passes some number of tests, you don't know whether it's correct. But it turns out there are many other techniques. One is explicit model checking, where you kind of explore the state space of the program on all possible inputs. Okay? So if you have small programs or communication protocols or something like that, that technique works. But the more interesting technique is this thing called counterexample guided abstraction along with model checking. Okay? It's actually counterexample guided abstraction refinement with model checking. In this technique, which is a very popular technique now, and it is very useful to it's very effective in proving programs correct. What you do is you start with your program and you build a model for it. Okay? And the model is an abstraction which defines more behaviors than the original piece of software that you had. Okay? But the model is much simpler. Okay? So this is something you need to grasp your head around. I mean, it's the software is more complex, but it defines a smaller set of behaviors. Okay? But the model is much more simple, but defines a larger set of behaviors. For example, your program could be computing the set of all prime numbers, and your model could be that it's computing odd numbers, right? If you forget 2, that's a valid model for that, right? So your model is very coarse, but it turns out that if you check your model and make sure that it satisfies safety specifications, then it turns out that the program also satisfies the specification you have. So the general idea is that if the program satisfies a safety specification, maybe there's a very simple reason as to why it satisfies that specification. Maybe there are a few variables which you need to track, maybe certain properties of the program you need to track, and then you can prove the program is correct. And there's a lot of other variables and junk going on there because the software is doing something useful. Okay, it's not just doing the software, that safety specification. So the idea of abstraction is to get the core of why this program satisfies that property you're checking. Let's say you're checking for buffer overflow property, right? You extract that model and then you check using that. And this has been very successful because, so one success story is Microsoft's tool called SDV or SLAM, which is a static driver verifier, which Microsoft ships as part of its driver suite, where people who use device drivers use this software to prove that their program is correct with respect to the Windows API, which Microsoft defines. So it turns out that Microsoft, the Windows device drivers work with the kernel of the OS, and if you don't follow the API, your system could crash. Okay? In fact, most Microsoft Windows crashes and blue screens are because of third-party software which interacts wrongly with the kernel. Okay, so they wanted to solve this problem, and so they've shipped out this checker, which is based on this tool, right? So once you get this model, you have to do a model checking, which is typically easier. It's a kind of explicit enumeration of the state space, right? And then model checking is very easy because the model is simple, right? And it uses that technique to actually prove device drivers correct. Okay. How many people know Floyd style, host style verification here? No? Okay. So this is the most general technique of how you would prove programs in the 50s and 60s. If you were actually trying to prove a small program correct, how would you actually go about proving it? It turns out that you can do this by giving assertions at every point in your program and loop invariants, and prove logically that your program actually satisfies the specification. Okay, this is a technique which does not. It can do very complex specifications, but it's very hard to automate. Okay, and of course on the left-hand side you have static analysis or data flow analysis, which is simple compiler static analysis like def use chains and so on, which are very, very shallow specifications, but they are very much more automatable. Okay? So counterexample guided abstraction refinement sits somewhere in the middle of the story. It can do not completely shallow specifications, it can do reasonably complex specifications, but it is automatable. Okay? Then there are these two other techniques, which is abstract interpretation and types, and these are like generated per property. Okay, so it's not a generic technique. It's really, if you wanted to, let's say, check a particular information flow security property that you had, you will build a type system for that. Okay, and all your reasoning, everything goes in the paper when you design your type system, right? And if somehow your program types, then you're through. Then you know that your property is met. But if your program doesn't meet the can't type check, then you don't know anything. Okay. Below there are two I forget this one. This one is the most important one. If you want to find errors in programs and you're not really interested in proving the program correct, or rather you're more interested in finding errors, then there is symbolic testing using SMT solvers is the most effective technology. And there are Microsoft tools again which can do this, called PEX, which is available in Visual Studio now, right? So it'll work for any .NET language. And the idea is that you do code coverage of your program, and the way it works is that it takes paths in your program and feeds the constraints on the path to a logical constraint solver and checks whether that path is feasible. So it will generate a test input which will drive you down that path. And using this technology, you can actually kind of get code coverage. And this is very, very effective in finding bugs. Okay. So the most important engines of software verification today are SMT solvers. There's no doubt about this. Logical constraint solvers are the most important technology that is advancing the field today, right? The reason is that a group of people have sat down and made constraint solvers to really scale. And SAT solvers, for example, which is an NP-complete problem, on program verification instances, you can use SAT solvers for 100,000 variables and 1 million clauses, and it will come back in 2 minutes. Okay, so it's an.
What do SMT stand for?
So SMT stands for Satisfiability Modulo Theories, which basically means that you have an underlying theory and you're doing satisfiability with respect to that theory. So, for example, for arithmetic, you can express constraints like x is greater than phi and y is equal to x plus 1 and y is greater than phi. Is that possible? Or is it possible that x is greater than phi and y equal to x plus 1 and y is less than equal to phi? Right? So you could ask such questions, and the solver knows arithmetic, and it can solve that constraint for you. So there's not only arithmetic, there's linear arithmetic, there's arrays, there's heaps, a bunch of logics which you need for program verification have been put together as constraint solvers. And there's no doubt that this is the biggest technology leap that we have found in the last 10 years. But there have been two other model checking heuristics. So once you get your model, right, there are two main techniques, which is binary decision diagrams and SAT solvers, which enable you to search the state space of the model. Okay. So that's just a high-level view of program verification. And now we come to this role of automata in software verification. So I think the role of automata in software verification, I feel, there are many of them. Okay, and the most important one is that they form the models of software. So I was telling you, in the abstraction refinement technique, what you do is you take your program and you then model it by abstracting away some part of your data, right? And what do you build? The model is an automaton, okay, typically, right? So they're best seen as automata, and we will look at some kinds of automata you get because of modeling software. There's also models of software behaviors. It turns out that even executions of software can be looked at as automata. We have done this for doing concurrency testing, but I will not talk about this particular one today. The other use I feel for automata are that they can represent interfaces for software components. Okay? Now these are not models of the software themselves, but models of how to use the software. Okay? It's a kind of dual notion. And automata also help in building interfaces for components. And finally, this is a weird application. It doesn't seem like a natural one, but it is in fact very compelling. Is that it turns out that if you want to reason about heaps, dynamic data structures which a program generates, you can look at the dynamic heaps as automata, okay? And you can actually reason with those heaps using automata theoretic techniques, okay? And I think this is a revival of the temporal logic automata connection for hardware. There's a revival of it in the software domain where logic on heaps can be, there's a close connection to automata. Okay, so we'll look at each of these ideas. Okay, so the first one is for software models. So as I said, abstraction-based verification. You extract a model from the code and you check the model, right? This is generally known as abstract interpretation, but a lot of static analysis was proved to be automata reducible, was reduced to automata analysis by, especially by Reps, Horowitz, and Segev. And there have been many success stories. I talked about SLAM, but another success story for abstract interpretation is Astre, which is a software developed in France for after the Ariane 5 crash. France invested in software analysis tools, and actually Astre has proved the entire control of Airbus control, flight control software to be correct for memory errors, completely using just abstract interpretation. So it's a fantastic feat. The reason we don't hear too much about it is that the software is not public. They don't release any information about it, right? But they sell the software, right? And but it's an incredible feat. Okay. So when you abstract a software as a model, what do you get? I claim you get automata. Okay. The reason is simple. You want to preserve the control structure which is in the software, right? And your data has been abstracted away into, let's say, x is equal to 1 or not, or some finite set of values you have which are predicates on your data space. So once you do that, you really have a finite number of states. The states represents the predicate on your data, right? But you still have to deal with the control in the program. So there'll be loops in the program, right? There'll be recursion in your program, and you still have to model that. And it turns out that recursive control can be modeled using a stack, just like a compiler uses a stack to do the recursion. You can use a stack, and therefore what you get is actually something called pushdown automata, which you know, I guess. So you have finitely many states, and the stack models the recursion. So model checking or reachability in your model really becomes pushdown automata reachability. Is a control state in your pushdown automaton reachable. And there are lots of tools to do this. I mean, the SLAM SDV from Microsoft Research has this tool called Bebop. There are other tools as well. But one of the things we noticed was that if your software or model is a pushdown automaton, what is your specification, right? And it turns out that specifications need not just be reachability in your pushdown automaton. They can be more complex. They can in fact be pushdown context-free properties themselves, right? They can be expressed as a pushdown automata themselves. The reason is that take a simple condition which is a horse-style pre-post condition. Okay, this is the standard way to do verification on your program. Is that I want to know whether whenever I call this method m, right, with parameters x and y, if a precondition p holds, I want to show that q holds when you exit the function. Okay. Now it doesn't look like it, but it is actually a context-free property, because unless you keep track of when you're calling m and when exactly it's returning, right, you have to match the p and the q according to this, right? So it's actually a context-free property. It's not a regular property you can state with a normal automaton. Okay. So then what the model checking problem really becomes is a context-free language is a subset of another context-free language, right? Because context-free languages are the ones accepted by automata, and that is undecidable. Okay, so already here you see that you can run into problems. You may not be able to even check your model effectively for all properties. But there is a wonderful insight that came through in about 2004. We defined this notion called caret, which was a temporal logic which could express things like horse-style pre-post conditions, and we were able to model check them. Okay, we were able to solve context-free language inclusion problem for this particular class of temporal logic formulas. And the crucial observation is that yes, your program has a stack, and yes, your specification has a stack, but it turns out that these stacks are not independent of each other. Okay, if you recall the horse-style pre-post condition, right, the call to m and then return to m is how the program works by using the stack. But also you have that your specification also uses the stack the same way. Okay, it's really synchronized with your program stack. Okay, and it turns out that that gives you actually decidability and actually efficient algorithms to do that. Okay, so we generalized this notion and said, okay, what are these context-free languages? And then we defined this thing called visibly pushdown automata, which I think is an automaton model worth knowing, independent of whether you're interested in verification or not. Okay, so consider pushdown automata where your input alphabet, right, is divided into three parts: call, return, and internal. Okay, every time you see a call letter, you must push into the stack. Okay, so the pushdown automaton does not completely control when it pushes and pops from the stack. If it reads a call letter, right, it must push into the stack. If it sees a return, it must pop from the stack. If it sees an internal, it cannot touch the stack. Okay, so the input determines how you use the stack. Okay, so this is good because then we can define the program behavior and the specification behavior over the same alphabet, and then they'll synchronize because they're working over the same words. Okay, and it turns out that you can define a class of called visibly pushdown languages, and it turns out this is an extremely robust class of context-free languages. It doesn't include all context-free languages, but it is extremely robust. It is closed under all Boolean operations, just like regular languages are. It is determinizable. It has decidable inclusion, and this automaton model, started a cottage industry of itself. Everyone who ever used context-free languages for program analysis looked at this again and said, "Oh my God, I have only a visibly pushdown automaton. I don't really have a pushdown automaton." Okay, and some open problems were solved, and lots of papers have been written on this topic, and I think it's a very, very useful notion. So software models are really visibly pushdown automata. Okay, now we come to this another way of looking at a visibly pushdown automaton, which will be useful, is that I'm going to look at it without a stack. I'm going to look at the automaton as without a stack, but reading this word which has these nested edges. Okay, so it's really, this definition of an automaton is really like a graph automaton. Okay, because I'm not reading a word anymore. I'm reading a graph where I have a word with nesting edges defined on it. It turns out that if I have these nesting edges, I don't need a stack. Okay, I can just have a finite state automaton working on this. So it will work on this. When at a push, it will keep the stack, whatever it wants to push to the stack, it will just store in its state. At the pop, the automaton is allowed to look at all the neighbors. So it will look at the previous state as well as the corresponding push state and update itself. Okay, so it turns out that visibly pushdown automata is really equivalent to nested word automata, which work on these nested words, and where the automaton does not use a stack anymore. You've compiled the stack into the graph structure, right? And then you can use actually a graph automaton for this. Okay. So this is useful for all kinds of things. It's also useful for XML, by the way, because these are really XML documents where you're matching open tags with the corresponding closed tags. So XML documents are really this.
Could you give a simple example of a language not accepted by visibly pushdown automata? I just want to get a sense of where it's a limit.
So if you take A to the I, B to the I, union B to the I, A to the I, then on A you must push or pop. I mean, if to accept A to the I, B to the I, you must push A and then pop B. But if you do that, then the second one will not get accepted. So when you model sequential programs, you get visibly pushdown automata or nested word automata. But when you move to concurrent programs, you have many processes, and each of them has recursion, so they have their own stack, and so you get multi-stack automata. You have pushdown automata which use multiple stacks, and emptiness is no longer even decidable. I mean, forget inclusion and things like that. Even emptiness is undecidable. So there have been actually various under approximations of concurrent models being proposed. One of them is bounded context switches, is that you assume that your concurrent program, you're running it only under schedules which run one process and then switch to another process, but then where the number of switches is bounded by a fixed constant k. It turns out that if you do that, then you get a decidable emptiness problem, but it's an under approximation. You're not searching the entire state space of the model, you're just searching it for a fixed k, the number of k context switches. But it turns out that most errors occur within k context switches, so it's still a good approximation. Right. I won't go into this. It also turns out that once you build these models, you can actually build very efficient BDD-based model checking algorithms, right? So we have a paper which actually does all those models. You can write. We have a formalism where you can write a model checker using, in about 2 pages, you can write down your model checker. Okay, I won't go into that, but it turns out there's a high-level logic to write your model checker. So you can, in 2 pages, you can write your model checker, and this actually beats all the model checkers out there, which have been written in C and Java. You can actually beat it just using a 2-page formula. Okay, but you can write uniform model checking tools for all these models, for bounded, for concurrent models, as well as sequential models. So I won't go into this one. It turns out that there are many under approximations of known. Okay, so one is k context switches, which I talked to you about. We extend it to something called k phases, where the restriction is this, that the pushdown automaton with multiple stacks is such that in every phase it has only k phases, and in every phase it can push onto one stack. It can push onto all stacks, but it can pop only from one stack. Okay, it's a generalization of k context switches, because k context switches means you have k phases, and in each phase you're allowed to use only one stack because you're in one process, right? It turns out that k phases is also decidable. There are weird classes of multi-stack automata which are decidable, extremely weird. Okay, there's one called ordered. Okay, so here's a pushdown automaton with k stacks. Okay, n stacks. Okay, and the stacks are numbered 1 through n. Okay, and the restriction is that you can push into any stack, but you can pop from the first non-empty stack only. Okay, and it turns out that this is decidable. Okay, so extremely weird classes of multi-stack automata are decidable, and we also studied software where the processes can communicate using messages. So if you can communicate with messages, let's say FIFO queues, then your automaton model then has a queue. Okay, not only has a stack, it also has a queue. Okay, and again it turns out there are very weird decidability results on when automata with stacks and queues are decidable. Okay, I won't go into all that. Each of them is a paper, right? But the uniform property is that extremely awkward definitions and very fragile. If you change one of these and say, okay, maybe I can push and pop from the stack, maybe I can do that, then the whole thing breaks and you'll get undecidability. Okay? So the natural question then we asked was that, what is this? What is this? What is happening, right? There are so many decidable classes, and there is so much awkwardness. Is there a robust common principle that explains why automata have decidable emptiness problems? Okay, and the reason I'm telling you about this today is because we have an answer. We have a general criterion that kind of uniformly describes many of these results, almost all the results that we know. And the answer is, in one line, is that all these automata classes which are decidable, it turns out that you can actually simulate them using graph automata. Graph automata is similar to the nested word automata I talked to you about. But you can simulate them using graph automata where the graphs have a special structure called bounded tree width. Okay? And it turns out that if you can simulate it with a graph with bounded tree width, it has a decidable emptiness problem. And all these classes are really trying to do that. Okay? So we have a very general result. And the graphs looks like this. For nested words, I told you the graphs have nesting edges, which model the stack. So you can model stacks using a set of nesting edges. And if you had multiple stacks and you were looking at a concurrent run of a program, then you can model it using multiple nesting edges. So the red is for process 1 and the blue is for process 2. And then if you had messaging, then what you have are, let's say, 2 processes. Okay? They have their local stack, which is modeled using these nesting edges. And then they have message edges, which go from a process to another. Right? So this is a send. This process is sending a message here, which is being received at this point. Okay, they don't cross because it's FIFO. Okay, so it turns out that automata working on these graphs can precisely capture the automata which is on the automata which work with stacks and queues and so on. Okay, you don't need stacks and queues. You can compile them away into graphs. And the crucial result is that the structure of these graphs tell you whether the emptiness problem is decidable or not. Okay? And this is the structure is that it has bounded tree width. So we have the mother of all decidability results for automata with auxiliary storage. We hope we have killed all research at this point. So let A be a class of automata with some auxiliary storage, stacks or queues, right? Then A has a decidable emptiness problem if we can simulate it using a graph automaton where the graph encodes the storage. So the automaton does not have storage. And the graphs on all possible behaviors, the graph is of bounded tree width. Okay? I'll just explain what bounded tree width is. And it turns out that all the mentioned decidable automata classes can be proved uniformly using this technique. So this will appear in POPL next year. Okay, so what a graph automata? A graph automaton is basically a tiling system. Okay, so remember, go back to the beginning of the lecture where I said automata are a way of defining an infinite set of objects. The infinite set of objects we have is now graphs. Okay, so how do I accept a graph? I give you a tiling rule. Okay, so for example, so if you know NFAs, right? It's really a tiling rule. What you're saying is that you must tile every node with a state. Okay, that's called the run. Okay, but you don't have to tile it going left to right. You can do any way you want as long as you tile it. Okay, so you tile it with states, and then there are some local conditions saying if this is Q1, if you tile it with Q1, and if this is A, then you can only put Q2 or Q3 or Q4 here. Right? So it's really a tiling condition on your graph. Right? And you can generalize this to a graph automaton which actually gives you tiling conditions. It says if U, A, V is an edge and you have tiled U with Q, then V must be tiled with one of these states. Okay? So a graph is accepted if it can be tiled, right? And so your automaton naturally defines an infinite class of graphs, those that can be tiled. So that's what graph automata are, right? And what's bounded tree width? It's a very technical notion. It was discovered in graph theory by Robertson and Seymour in a very fundamental paper on minors. But essentially, what it is it's a number. Okay, given a graph, it's a number which represents how close the graph is to a tree. Okay. Now, how do you define it, right? So the idea is that suppose this is your graph, right? Then I'm looking for a tree, okay, where every node in the tree is a bag, has a bag of vertices, okay? So this node has A, B, C, those 3 vertices there, okay? And I have a tree with these bags, okay? And the idea is that every edge must be in a bag. So if I take CB, there must be a bag which contains both C and B. Okay, and all bags that contain a particular vertex must be connected. So if I look at C, these bags have C, right? And there's a connected, right? So you can't use C again here without using it here. Okay. Now it's a weird definition, but it turns out that it kind of corresponds to how close it is to a tree. So the width, the number, is the number of elements you need to use in your bags, minus 1. Okay. So this is called a tree decomposition. So find the tree decomposition which uses minimal bag sizes. That gives you your tree width. Okay. Yeah.
So if you have a bag, then all the edges must actually exist in the graph?
No.
They need okay, not. So it can be a superset.
Yes, it can be a superset. So the tree width of a decomposition is the largest bag in the tree, and the tree width is the minimum over all tree decomposition of the tree width of the decomposition, minus 1. Minus 1 is just a technicality. So the tree width of a tree happens to be 1, okay, which is why 1 minus 1. You need 2 elements per bag. So tree width of a tree is 1. The tree width of a cycle is 2. Okay, it turns out that what you need to do for a tree, okay, I can explain this actually in a different way, this decomposition. It says how many fingers do I need to construct this graph, okay? So I have ABC, I have 3 vertices, okay, and then I can draw edges between whatever I have, okay? So I draw AB, I draw AB edge, BC, and AC. So I have this, right? So I have 3 positions, 3 fingers on this graph, right? And then I can remove 1 finger and add one other finger. Okay? So I can take my hand off A and then I add E. And then I can put edges between the vertices that I have. Okay? So that's the intuitive description, and it turns out that so for a cycle the tree width is 2 because I can put in edges in a cycle by just going forward. Right, but in the end I must connect the first vertex to the last, so I need to remember the first vertex. So I need 1 more vertex I need to keep so that I can put it in the end. So I get tree width 2. Nested words of tree width 2. In fact, that's why pushdown automata have a decidable emptiness problem, is actually because they have width 2, okay, a bounded width. It turns out that what is not of bounded width, if you take the set of all cliques, a k clique has width k minus 1. Okay, if every vertex is connected to everything else, you can't really take off something. You can't take off your finger, right? So a set of all cliques have unbounded tree width. And the theorem is that all these graphs, if you look at the restrictions which you put in order to get decidability, it turns out that they are bounded tree width. Okay, for example, if you have only bounded number of context switches, the tree width is order k, right? If you have k phase, it's 2 to the k, and so on. So all these graphs, along with the restrictions, give you bounded tree width, and this gives you a kind of general principle of how you look for automata with decidable emptiness problem. Forget the stacks and queues, and don't get mesmerized by that, right? Just represent it as a graph and try to maintain the tree width to be bounded. So I'll skip this result, the details of this, and move on to the next one. So the summary of the first thing is that if you want to build models using abstraction from software, then you get automata. So very, very, very natural application of automata theory. But the automata can be very complex. In order to capture the intricacies of your software, especially control, you need to have stacks, you need to have queues, you need to have distribution, right? But we have a general result which tells you when these models will be decidable, and also build the appropriate algorithms for them. So the next thing I want to talk about is automata modeling interfaces. And this is slightly different. It's the dual notion where you're not trying to model the software, but you're trying to say, how do I model the environment on which the software assumes? Okay, so for example, this is the environment for a particular Java class in java.security. So it turns out that this class has methods, right? These are the methods in the class, right? Init sign, init verify, and so on. And it turns out that the class kind of assumes that you will use it in this particular way. Okay? So you must first init verify or init sign. You must initialize one of them. And this is the verify mode, and this is a sign mode, right? You can switch between them using init sign and init verify, right? But here, when you're here, you can update verify or init verify. But when here, you can't verify. You can only update sign or init sign. This is some cryptographic protocol. Okay? It's a cryptographic class, right, where you can sign and verify. So given a Java class file, these restrictions on how to use this file, this class, is usually given in terms of English comments in front of your file. And what we'd like to do is actually mine this specification from the code automatically, because then we can verify the client classes whether they actually conform to these. If you don't follow this protocol, it will give you an exception, and your software can crash. So automata serve as extremely natural models for interfaces as well, right? And once you mine these interfaces, you can actually have. So we did this using automata-based learning. So I told you that automata also gives you learning algorithms. So using learning, we actually were able to synthesize interfaces for Java classes, right? And but once you mine these interfaces, you can also use them for other things. So we've used them for compositional verification, where if you're checking A parallel B, checking both together, A and B are complex programs working in parallel, computing verifying A parallel B simultaneously is very hard. So what we do is actually synthesize an interface I, such that A generates, so the I captures the interface between A and B. Okay? So A is very happy with I in the sense that it can meet I, it conforms to I. And B with I is also safe, right? So it turns out that you can generate interfaces which are much smaller in size than A or B, and by doing these two checks, since each of them involves only A and I or B and I, you can actually do this much faster than normal model checking. Okay? So this is this also uses learning theory of automata. Okay? And finally, I come to this this topic of how to use automata for logics on heaps. Okay? By heaps, I mean dynamic data structures created by a program. So think of lists or trees or binary search trees, and so on. So as I told you, SMT solvers are logical theories, automatic theorem provers for certain kinds of theories. But it turns out that logical reasoning for heaps don't really exist. Okay, the technology for reasoning with even trees is not there. Okay, so it's very complex because of several things. One is that the domain of which you're dealing with is an arbitrarily, it's not bounded. Okay, you're not looking for k integers, right? It's a dynamic data structure. If I say, is there a list which satisfies this, I have no bound on the size of this list. And it also turns out that any logic which works on data structures requires quantifiers, because even if I want to say a list is sorted, right, I need quantifiers in my logic, because I want to say that for every x, this x and successor of x are sorted, right, or is less than equal to the successor. So you need a quantifier, and it turns out that most of these logics do not support quantifiers. Okay. Not only that, I want a data structure, but I also want to reason with the data contained in the data structure. There could be integers in your data structure, like a binary search tree has integers in your data structure. And you have to reason with that too. So you have to really combine graph logic, right, with the data contained in the nodes, which are integers, right? And it turns out that there are no general combinations of logics which have quantifiers. Without quantifiers, all these logics are combinable. You can take arrays of rationals or whatever you want, and they're combinable because of this general Nelson-Open combination, which allows you to combine quantifier-free theories. But if you have quantifiers, you're dead. You can't do combinations. So, but SMT solver is extremely useful. So this is a slide from Microsoft Research, which is the set of tools within Microsoft Research only that use Z3, which is the SMT solver. Okay, so SMT solvers are an engineering abstraction of logical reasoning, right? You don't do your logical reasoning yourself. You always call an SMT solver, so that if your SMT solver, the SMT solver engineers are way better than you in doing the engineering of the logic, right? So they can do much better, and your tool will improve because you use the SMT solvers. Okay, so all these tools will improve if you improve Z3 theory by some notch. Okay, and some of the PEX and SAGE actually the symbolic testing tools. SLAM is the verifying tool for drivers. There are all kinds of things in this picture, and this is within MSR only. There are probably 20 more tools outside MSR that use Z3. Okay, so the key thing is that we have defined a decidable logic for heaps that uses automata theory. And again, the idea is very simple, is that if you're talking about an invariant in your program and you're saying the list is sorted always till this pointer, okay? You have a list and you have a pointer into the list and you're saying from the beginning of the list to this pointer, everything is sorted, right? But that's a set of graphs, right? That's a set of graphs which represent the set of all lists which are sorted, right? And it turns out that using automata theory, you can express the class of all graphs which form your invariant in your verification. Okay, so automata can express infinite collections of heaps. Okay, and this is not a new idea. It was actually an old idea by Muller and Schwarzbach, where they showed that you can actually do this, but they didn't have the underlying data theory which they can combine. So, for example, the binary search tree is you'd like to state such a property, right? You would say for every y1, y2, right? If y2 is in the left branch of y1, then the key is less than that, the root. And if it's in the right branch, then it's greater than or equal to that. And you'd like to say such a property and ask this SMT solver, is there a tree that doesn't satisfy this or satisfies this? So our graph logic is made of two parts. You can have any arbitrary recursive data structure. So you can define lists, you can define trees, but you can define a general class of recursive data structures. These are like graph types, if you know about graph types. And essentially what it is made up of a tree, okay? So you're recursively constructing this data structure, so it kind of looks like a tree, right? But you can have any kind of edges between the nodes in the tree defined logically using monadic second order logic, which I will not talk about, but it's a particular logical way you can say that there's a link between two nodes. Okay, so you can define, this is an example where you have a tree and all the leaves are linked by a linked list. Okay, and this is actually definable using recursive data structures. And then on this class of recursive data structures, we have a formula which is of this kind. It is an existential quantification over nodes, followed by universal quantification over nodes, and then a formula, right? I won't present this one, but no, actually. So the decidable procedure works as follows, right? The set of all models that satisfy your formula is this set, right? And what you can show is that there is a finite set of minimal models, right? Which will already, if your formula is satisfiable at all, these these graphs will satisfy it. Okay. So what you do is you combine an automata-based, graph automata-based algorithm for finding out the set of graphs, which are your heap graphs, right? And then you take these graphs and feed them to your Z3 or some integer solver asking whether is there a way to fill these data structures with data so that I can actually find a model. If this does not happen, if you cannot, then I know the formula is not satisfiable because I've pulled out the minimal models according to this satisfiability relation. Okay, it's more complex than that, but that's the high level idea. So we have a syntactic decidable fragment as well. I won't go into it, but basically there are elastic relations, where elastic is a technical concept, and there are non-elastic relations, and the syntax is defined with respect to that. But what it is really a powerful SMT theory for heaps, right? Which uses automata to deal with the graph structure, right, of your logic, the nodes and how they are connected, how the pointers connect them, and then using this small model theorem, you combine it with an integer theory, right? And this is probably the first the most general SMT combination of combinational theory I know for heaps. Right? So this once you have such an SMT solver, you can use it for all kinds of purposes. For example, you could do input generation, symbolic input, test input generation, where you're actually feeding in as inputs heaps. Right? You can say, is there a binary search tree which will make this program execute in some assertion failure. Okay, so I'm done. So the main thesis that I want to propose is that automata theory will play a key role in software verification in these kind of 4 domains. One is that it can model software very naturally. It can model software executions naturally. I didn't go into that, but it turns out you can do that too. It can model interfaces for software components naturally, because the method call interfaces, and is also very useful for deciding constraints on heaps. Okay, so I think these will be the key algorithmic techniques driven through automata that will play a role in software verification. Thank you.